Well, I think it's a good time to pause and just think about what we have. So this sort of gives us a summary of our various tests that we've learned about. So we have our go-to series, our p-series and geometric. And we're going to compare lots of series to these, and so we want to make sure we have those down cold. So p-series means you have 1 over n to the power of p. That converges when p is above 1. Geometric series means, well, we're geometric. Means we have some number raised to power n, and that converges if our number is smaller than 1. So we have a couple of tests. We have the nth term test, which says if our terms don't go to 0, the sum has to diverge. So that's really good when the terms don't go to 0, and sometimes it's obvious, sometimes it's not, but we just have to check. And it's a weak test in the sense that it's hard to make a lot of conclusions, but when it works really easily. There's the integral test, which says, hey, we can relate the sum to the integral. Now the function has to be nice, it has to be continuous and decreasing. If that's not true, you can't apply the test. Now in some sense, the integral test is kind of the weakest of the tests, because it's really highly specialized, especially now that we have p-series. So the integral test was helpful when we used it for p-series, but I will say it's a very limited application. We will see it pop up later on today, but in general, we're not going to see it pop up very often. Then we have a comparison test. And the comparison test says, well, let's take a look and compare things. So, well, how does it work? Well, we have two sequences. They're non-negative. And we say, okay, a sub n is below b sub n. And now we say, look, if b sub n is small, so small enough so that the sum converges, then a sub n has to be even smaller, so it also converges. On the other hand, if a sub n is somewhat large, in the sense that the sum of a sub n diverges, then b sub n has to be larger than that. Well, that's if you're even bigger than infinity, you're infinity. All right. Then we got to things which are a little bit more sophisticated, which is the limit comparison test and the ratio and root test, which they both involve limits. In the limit comparison test, you have, again, two sequences. You want them to be positive, a sub n over b sub n, and you look at the limit as n goes to infinity of an over bn. And what we're trying to say is if we have this limit, and it exists, and in particular, will almost always be in our first bullet point. And that says, look, if you have that limit, and it's less than infinity, L is some number, not 0, between 0 and infinity, all right, it converges, then you can tie the two of these together. Now, what does this do for us? Really, you should think of the limit comparison test as, you can do it as sort of clean up the noise. And in other words, if you have a lot of extra terms which are distracting and hard to work with, we can go through and say, look, we don't actually need all those pieces because ultimately their contribution is very minimal. Focus on these other parts where we actually get some real important growth. And so that's what we're going to use the limit comparison test, is clean up the noise. In particular, if you see lots of things being added or subtracted, that's a great time to pull out the limit comparison test. Now the ratio or root test is a little bit simpler because notice that in the limit comparison test, we usually have like the a sub n, but we don't know the b sub n before we start. And so we have to come up with it. In the ratio and root test, you don't have to come up with anything. So what you do is you look at either the ratio of the next term to the current term, an plus 1 over an, or you look at the nth root of your term, an, and say, what happens in the long run? Let's suppose it converges. If it converges to a small number, then the whole sum converges. If it converges to a large number, then the whole sum diverges. Small and large being, are you below 1, are you above 1? If you're equal to 1, use a different test. Now, I will say that the ratio and root tests are going to be supremely important to us especially going into next week and as we head off towards the end of the semester. So the ratio and root tests are going to be very important to us. And then after we get past the ratio and the root test, we're probably going to have to deal mainly with things where we're doing p-series or geometric series to sort of finish the job. And that will make more sense as we go on. So the goal for today is just to say, let's practice some of these different ideas and try out some series. And we're going to ask ourselves a lot of questions. Do things converge? Do things diverge? So let's just go ahead and get right into it. All right. So, example. Determine if the sum from 1 to infinity of 1 over 3 minus sine of n to the power n converges. Now, you might think, aha, idea. Look, I see everything here is raised to the nth power. So, if I see everything raised to the nth power, we can say root test. So, let's pull out our root test and see what we get. So, root test says what? Well, we're going to take the limit as n goes to infinity of 1 over 3 minus sine of n to the nth power to the 1 over nth power. Well, now because this is to the n, that's to the 1 over n, that's 1 over 3 minus sine of n. Oops, and I forgot to write my limit down. That's really bad. You should keep writing down the limit until you actually take the limit. Now, what happens as n goes to infinity to 3 minus sine of n? What does it do? What does it do? It actually, the problem is that sine of n doesn't settle down. It moves up and moves down. So 3 minus sine of n, it's not going to a fixed number, it's moving around. So this limit, it doesn't exist. Now, what does that say about the root test? Well, it really says that the root test is out because we have to have a limit for the root test in order to apply the root test. There is no limit here. So we're in trouble. Now, if you go further on in mathematics, which of course everybody wants to go further on because that's what all the cool people are doing. But if you go further on, you get into saying, well, maybe we don't really need a limit. Maybe we need like a lim sup or lim inf. And that sounds really fancy when you add those words on. So we're not going to go into that. But let's not give up completely here. Let's think about sort of why we failed. The reason we failed is this is not converging. But let's think about our denominator. 3 minus sine of n. What's true about that expression? And in particular, whenever you see a sine, you should say, well, that's just moving up and down. So 3 minus sine of n. What's the smallest it can be? What's the largest it can be? Well, smallest it can be is if I had sine of n be a big number. So it would be 2. Largest is 4. So 1 over 3 minus sine of n. Well, what's the largest that can be? Well, if I want 1 over 3 minus sine of n to be large, I say, let's make the denominator small, which means it's below 1 over 2, and it's above 1 over 4. By the way, this is good news for us. This tells us that we're never going to be dividing by 0. That's always a little bit of a concern we have. When we make mistakes, usually we put our index in the wrong place, so we get a divide by 0. But not today. Not today. All right, so what's the point? Well, see, we're kind of like building up to that. We say, all right, well, let's take everything and raise it to the nth power. So 1 over 3 minus sine of n to the n is below 1 over 2 to the n, and it's above 1 over 4 to the n. Now, wait, look. This is like we're starting to compare things. And we start to say, okay, well, what do we know about these sums here? Well, they're both geometric. Now, this sum, that's going to converge because it's like 1/4 to the n. But what about that one? Well, that also converges because it's 1/2 to the n. Now, suppose that we have this information. Which one of these is important? Is it useful that 1/4 to the n, which converges, is below this? Or is it useful that 1/2 to the n, which converges, is above our summand? Which one matters? Well, we want to have it, if we want to compare it to a convergent thing, we always want to have the convergent thing be above what we're after. So now we're almost there, right? We say, hey, here's the idea. In fact, we'll just try it over. Let's do a comparison test. So a comparison test says we have that 0 is below 1/3 minus sine of n to the n, which is below 1/2 to the n, and the summation from 1 to infinity of 1/2 to the n converges because it's geometric. We know when geometric sums converge. Then our conclusion is the original sum of 1/3 minus sine of n to the n also converges. So yes, that converges. Good. All right. And this is, by the way, why it's good to have more tests. Because sometimes you'll run into unusual situations where the obvious test fails for some reason. So here the root test fails because the limit didn't exist. But we were fine. We had a backup. So, all right. Well, let's try another one. Example. Does the sum from 100 to infinity of 5n plus log n plus 200 over 3 log n minus 5 cubed times n squared minus 0.2 to the n plus 200 converge? Oh, wow, okay. What a question. All right, now, what do we do? Well, at this point, it seems really intimidating. Why? Because there's noise. There's all this extra stuff floating around, and we're like, it's really hard to maintain that. But where there's noise, there's a way to clean up the noise. Now, that's where the limit comparison test really shines. And the way we use the limit comparison test to clean up the noise is we go through and we ask ourselves some basic questions. Namely, what's causing things to get big? So, in each set of terms, there's a term up here in the numerator, and there's really two terms down here. Let's go through and identify which term is important and which term is small in the long run. So upstairs, 5n versus log n versus 200. Which one is going to cause it to get big? Well, the 200 doesn't ever change, so that's going to not really make it get big. Log n goes to a big number eventually, but definitely not as big as 5n. So 5n, that's the important term up there. How about this one? You have n squared minus 0.2 to the n plus 20. Now you might think, hey, exponential often wins, but be careful, exponential can also win the race to 0. So look at that. See how it's 0.2 to the n? What that tells us is that when n gets big, this number gets small. And 20, of course, is just 20. On the other hand, n squared is getting big, so that says from that term, it's the n squared. That's the part that's getting big. Now, how about inside of this set of parentheses? Well, 3 log n versus 5, obviously it's the 3 log n. That's getting big. And of course, don't forget the fact that it's being cubed. Okay? So, what does that say? Well, what this is saying is the following. It says, if you think of this expression right here as your a sub n, then what you'll do is you'll let b sub n equal 5n divided by 3 log of n cubed times n squared. Now, by the way, if you don't want to take the constants along, you don't need the constants. They they just will work themselves out. So in fact, let's just go ahead and get rid of the constants, because constants, we're really worried about growth. Constants don't really affect growth. So we're going to think of it as n over log n cubed times n squared. Or, if you like, we can think of this as really 1 over n log of n cubed. Okay, so there's our b sub n. Now, what's our claim? Well, our claim is these sums are going to be connected. So, in other words, I really have a different sum, which is the sum n equals 100 to infinity of 1 over n log of n cubed. All right. So, again, these should be connected. So now we have to justify that. And the way you justify it is you do the limit. All right, so take the limit as n goes to infinity of our a sub n over b sub n. And by the way, if you just always grab the highest power terms, the limit's going to be exactly what you need it to be. But we're going to go ahead and do this exercise because it's good for us to practice and to see why this works. So 5n plus log n plus 200. Divide that by, and then we're going to have 3 log of n minus 5 cubed times n squared minus 0.2 to the n plus 20. And now we're going to multiply by the reciprocal of b sub n. Okay, so what is that? Well, I can think of the reciprocal of b sub n as, and I'm going to use this form here, all right? So, in other words, before I did my simplification, so the reciprocal of b sub n, as I'll just take the reciprocal of the top, 1 over n, and then the reciprocal of the bottom, 1 over log n cubed, 1 over n squared. And the reason I'm going to do that is I'm going to now multiply the reciprocals into each appropriate part. So in the top, we get the following. Well, we'll get 5 plus log n over n plus 200 over n. The 1 over log n cubed, because it's a cubed, I can bring it in, and it's like I'm putting log n inside of there, and if I divide, I'll get 3 minus 5 over log n cubed, and then the n squared I bring in, and I'll get 1 minus 0.2 to the n divided by n squared plus 20 over n squared. Now here's why this all works. Now we're ready to see it. Remember that we said on each term, you pick the term that grows fastest. So what happens is that the parts where I was growing fast are now just numbers. The parts that weren't growing fast, you have a slow growing thing over a fast growing thing. So that will go to 0. 200 over n goes to 0. 5 over log n goes to 0. 0.2 to the n over n squared goes to 0. 20 over n squared goes to 0. So all these terms go to 0 in the limit. And what's left is the things that came from our fast terms. Namely, we get 5 over 3 cubed times 1. Now, I don't care what that value is. This is not the ratio test, it's not the root test. All I care about is that it's a limit that exists and it's not 0. So, our moral is, now we have that by limit comparison, we know that both these series will converge or diverge. So now, instead of having to deal with the original series, which had a lot of noise, now we can deal with sort of this simplified one, which is more straightforward. Okay, so we come to this question. Does this integral converge or does it diverge? Well, what does it look like? Well, if we ignore that log n cubed, that's 1 over n. That actually is a very famous sum. That's the harmonic sum. And we know the harmonic sum is going to diverge. But now we have a little bit extra. Now log of n is not very big. Log of n cubed is not very big. is that little bit extra just enough to tip us over the edge? Well, it's not so clear. It's not so clear. So, what do we have? Well, what's the right test? Well, pretty much we're going to go and apply the integral test. The integral test is almost tailor-made for things that look like this. So in other words, 1 over n times maybe log n to a power, or 1 over n times log n times log n to a power. That's almost the only time we see integral tests now. So now we're going to apply the integral test. So integral test says that both this sum and this integral, 100 to infinity of 1 over x log x cubed dx, both will converge or both diverge. So what we've done is we've sort of done two steps. We've limit comparison and integral says, lo and behold, if I want to know whether this converges, I have to answer the question, does that converge? Well, now we're getting a little bit more comfortable. We're back into our integral world where we've had more time and more practice. Okay, so can we integrate 1 over x times log x cubed? And how do we do it? Well, if we would put on our Calc 1 hats, we say, well, I see a log x on the inside, so let's try a substitution. So we try substitution u equals log of x. What's the derivative of log? 1 over x. Ah, perfect, right? Why? Because look, we have a 1 over x and a dx. Exactly what we needed. So this is the integral of 1 over x dx becomes our du on the end. And then the log x cubed becomes a u cubed. Now, the bounds. Log of 100 is log of 100. Log of infinity, well, we don't really mean log of infinity. What we really mean is what happens to log as x goes to infinity, the input goes to infinity. And it still goes to infinity. Okay, so it's still improper. But now it's an improper integral that's a little bit easier to digest. Now the way we usually do this integral is write this as u to the minus 3. All right, so we're getting close. What's the integral of u to the minus 3? Well, you add 1 to the exponent, so that would be u to the minus 2. Then you divide by the exponent, so that would be divided by minus 2, which makes it a minus a half. And then we're going to evaluate from log of 100 to infinity. If you like, this is the same as minus 1 over 2u squared, evaluated from log of 100 to infinity. Now, this is the important part, the infinity part. What happens as we let u go to infinity to 1 over 2u squared? It goes to 0. Then we're going to subtract minus 1 over 2 times log of 100 squared, but we really don't really care about that last part. This is the important part. The important part is that as we let our value go to infinity, we get something which doesn't blow up. So that says our integral converges. And now we're ready to backtrack. We know the integral converges. Integral test says that this sum converges. This sum converges. The limit comparison test says this sum converge. So our final conclusion is, does it converge? Yes. And we needed to use a couple of tools. But I like to think of the limit comparison test as really a tool that says, hey, let's make things simpler. Let's empty out our noise and make our life better. Because that's a good thing to do. All right, next problem. Determine if the sum of n equals 1 to infinity, n to the power n plus 1, divided by 2n plus 1 to the power n converges. Okay, well, you could probably do a lot of things here. And the reason you can do a lot of things is a lot of things work. But, well, I think ratio test and root test should be sort of our go-to standards. And here you'll see that we get lots of n's up in the exponents. And so that's an indication that a root test could work pretty well. So let's try a root test. So let's think of this as our a sub n. So if we look at the limit as n goes to infinity of a sub n to the power 1 over n, well, that's the limit as n goes to infinity. We have n to the power n plus 1. Divide that by 2n plus 1 to the power n to the power 1 over n. Now, n to the power n plus 1, let's just make a little note here. That's the same as n to the power n times n to the power 1. So, if I I take this power in, then what I can do is I can really say it's the following. I can think of it as n to the n to the 1 over n is just n times n to the power 1 over n. And I'm going to divide that by 2n plus 1 to the n times 1 over n, because I'm going to multiply these exponents together, so 2n plus 1. Now, let's think of this as really two pieces. So this is the limit as n goes to infinity of n over 2n plus 1 and n to the 1 over n. What happens to these pieces? Well, n to the power 1 over n, that's a really important limit and one that we should know by heart. What happens to n to the power 1 over n? That goes to 1. How about n over 2n plus 1? Now, we may not necessarily know that particular one by heart, but that type of limit is something we should be comfortable with and something that we should recognize what to do. What do we have? Well, what we have is we have a polynomial over polynomial. When you have polynomial over polynomial, what you do is you say, all right, let's look at leading coefficients. So in our case, what's the leading coefficients? It's 1 over 2. So that goes to a half. All right, so what's our limit? Well, our limit is going to be a half times 1, which is a half. Good. Well, now, what are we doing? Well, remember what test we're in. And it's important to remember what test you're in because depending on the test, you do different things depending upon what the limit is. So we're in the root test. In the root test, what we do is we compare this number to 1. Well, a half is less than 1. And therefore, what we get is that this will converge, right? Because that's smaller than 1. So this converges. So there you go. Now, well, we're going pretty slow, so we can do another limit. This is another one that's a little bit fun. So let's see. What if we had the sum n equals 1 to infinity of, say, arctangent of n, divide that by 2 to the n, and, let's be careful here. Sum n equals 1 to infinity, arctangent of n to the n, and then that's divided by 2 to the n. Because, it's been a couple of days since we've mentioned arctangent. I'm having my arctangent withdrawal. So I gotta throw it in. Okay, well, what could we do here? Well, what's the right test? Well, everything's raised to the nth power. So this is, again, a root test. So this becomes a limit as n goes to infinity, a sub n to the 1 over n. Well, that's the limit. N goes to infinity. If we take the top and bottom to 1 over nth power, we get arctangent of n over 2. Now, what happens to arctangent as n goes to infinity? Do you remember? Well, arctangent, if you were to sketch it, it does that type of thing. It actually approaches a very specific value. And the value it approaches is pi over 2 as you head to infinity. So this is pi over 2, which is pi over 4. Well, what's true about pi over 4? Well, pi, it's 3.14, right? Remember the old chant? Cosine, secant, tangent, sine, 3.14159, right? So about 3.414. So if I divide it by 4, that's smaller than 1. And therefore, we can conclude by the root test, so by the root test, this sum converges. All right, good. Okay, well, let's do one more problem for today. Okay, so this is kind of a different type of question because it doesn't say, does this sum converge or diverge? It says, well, determine for which values of r positive that this sum, k equals 0 to infinity, of k factorial squared over r to the k divided by 2k factorial converges. All right, so that's a different kind of a question. So it's like we're trying to say, well, let's pick a value for r and let's see when this converges or when this diverges. All right, well, let's dig into this. So first off, what's the right test to use here? And there should be a clue. And what's the clue? Well, the clue are these little symbols here, these exclamation marks, the factorials. When you see factorials, that says you should think ratio test. So we see those factorials and we put on our ratio test hats. So we're going to think of this right now as our a sub n. Oh, a sub k actually, yeah, because we changed our index. By the way, changing your index, it's okay. You can change it. It doesn't matter that it's a symbol n or it's a symbol k. Same philosophies. So we're going to look at the limit as n k. It's the same philosophy, but it is hard to break habits, I will say that. But, well, practice, right? ak plus 1 over ak. So we're going to take a look at the limit as k goes to infinity. So ak plus 1, this is the part where you got to be careful. So what happens here is we want to, for every single value for k, we want to replace it by k plus 1, but we want to make sure we do it in the smart way so we don't miss anything. So that's the time when it's good to be extra generous with your parentheses. So we're going to have k plus 1 factorial squared r to the power k plus 1. Divide that by 2 times k plus 1 factorial. Okay, so everywhere we saw a k, we replaced it by k plus 1. And now, what's our a sub k? Well, we're just going to flip it over. So 2k factorial. And then we're going to divide that by downstairs k factorial squared. And then r to the power k. All right. Now, oftentimes it's helpful to see what's going to happen next by doing a little bit of regrouping. So, for instance, I'll have the k plus 1 factorial squared. I'm going to put underneath that, I'm going to put the k factorial squared. I'll put the next factorial, 2k factorial. Divide that. Here I'll go ahead and multiply the 2 through. So that's going to be 2k plus 2 factorial. And then the last part, that's r to the k plus 1 divided by r to the k. Now we start saying, can we simplify things? Well, there's at least one easy thing, the r to the k and r to the k plus 1. Okay, so we're just left with a single r at the end. All right. Now, how about the factorials? Now, this is why the ratio test works so great. what you can do is you can pull terms off the start. So this becomes the limit as k goes to infinity. Here, we're going to get k plus 1 times k factorial squared divided by k factorial squared. And the next term will be 2k factorial. Downstairs, we're going to keep pulling terms off. Well, not very long. We're going to pull off 2 terms. The plus 2 is the clue that it's plus 2. The 2 terms that we pull off. 2k plus 2 times 2k plus 1 times, then what's left is a 2k factorial, and then the last term is the r. The 2k factorials cancel, the k factorial squareds cancel. So what do we have? Well, we have that this is the limit as k goes to infinity of, well, we have k plus 1 times k plus 1 times r. Downstairs we have 2k plus 2 times 2k plus 1. Now, let's be a little bit careful here. What can you do? You can actually simplify this a little bit more if you wanted to. Hey, look at this. K plus 1 and 2k plus 2. What does that become? Well, if you factor the 2 out of here, you get 2 times k plus 1, which means that this whole thing equals 2. So we have that part equals 2, so we have a limit as k goes to infinity of 2. Let's be careful, Steve. Okay, k plus 1 times r. Downstairs we have 2 times 2k plus 1. Okay, now we're ready to take our limit. Okay, good. In fact, the limit's super easy now, because what do you see? Where do the k's show up? We've simplified it so far that there's only a single k upstairs and a single k downstairs. And so when we take this limit, we say, okay, well, look at the leading coefficients. So what do we have? Upstairs we have, it'll be r, and downstairs it'll be 4. Because 1 times r, 2 times 2. Now, what do we know? Well, we're doing what test? Well, we're doing the ratio test, because that's what we have. Now, the ratio test says if this is less than 1, it's going to converge. If this is bigger than 1, it's going to diverge. And if this equals 1, this is going to leave us with some question marks. So, right now we know the limit is r over 4. So that tells us a couple of things. So we know for sure if r over 4 is less than 1, it converges. And we know that if r over 4 is bigger than 1, it diverges. Well, of course, r over 4 being less than 1 is the same thing as saying, what? If r is less than 4, it converges. R over 4 bigger than 1, same thing as saying as r is bigger than 4, it diverges. So we're pretty close to knowing everything. Almost everything. In fact, what don't we know? We know that it's going to converge, starting at 0 up to 4, but not including 4. And then from 4, but not including 4 on, it's going to diverge. So the last question is, what about equals 1? Okay, we got to get into that. So let's think about that case. Okay, so let's focus on the r equals 4 case for just a second. Now, to be fair, the ratio test will technically fail us, but let us go ahead and look at the last step here. Let's look at the limit k goes to infinity. Well, I won't look at the limit. I'll look at ak plus 1 over ak. Now, if we're in r equals 4, that says what? That's equal to k plus 1 times 4 over 2 times 2k plus 1. Why? Because that's what ak plus 1 over ak is. See, the only thing we've done from there to there is just simplifying the expression. We haven't added or taken away anything. Now the 2 goes into the 4, leaving with the 2 upstairs. So that's 2k plus 2 over 2k plus 1. Now, quick question. If I have 2k plus 2 over 2k plus 1, what can I say about that value? Now, I can definitely say in the limit it's about 1, but I can say something a little bit better than just that. I can say it's actually bigger than 1. Right? Because to go from 2k plus 1 to 2k plus 2, I add 1 more. And that plus 1 says that the numerator, it's slightly larger. So what does that say? Well, it says that ak plus 1 is bigger than ak. Now, why is that important? Well, in other words, our sequences in terms of our sequence, I'm talking about the ak, the sequence of the a sub k increases. Now, why is that important? Well, let's look at k equals 1, right? Or even k equals 0. K equals 0 is what? We're going to get upstairs 0 factorial is 1, 4 to the 0, which is 1, and 0 factorial, which is 1. So what happens is our a0 equals 1. Well, that's going to be less than a1, that's less than a2, that's less than a3. And the reason I can write these is I always know that the current term is smaller than the next term. So what does that say happens when we look at our terms as we head to infinity? Well, what happens is for r equals 4, the limit as we go to infinity of a sub n, it has to be bigger than 1. Now, I don't know if it converges or not, but I know for sure it's bounded below by 1 because a0 is 1, it's the first term, and everything else keeps getting bigger. Now, if the limit doesn't go to 0, what's our conclusion? Our conclusion is, by the nth term test, we see that the sum has to diverge. All right. Now, that tells us that we can finally figure out, in that case, we didn't really use the ratio test, but we sort of said, can we extract a little bit more information? Now, in general, it's really, really hard to do this, but in a few cases we can. We're going to develop a sort of a general methodology, and this problem is a hint of things to come, where we're after, well, when does it converge or when does it diverge? So our answer is, this will converges for 0 less than or equal to r less than 4. And that's the answer. And then for 4 on up to infinity, it's going to diverge. So, all right, good. This last part is a little bit subtle. Focus on the first part here where we said, okay, we applied the ratio test. When is it less than 1? When is it bigger than 1? We're going to be doing that a lot in the next week. Now let's just take just a second and mention where are we going and what sort of remains to be done. Well, the next thing that we're going to tackle is if we come back to our collection of tools, you might notice that there's sort of an underlying assumption we've been making at many places. You'll notice that in all of these places, there's this sort of implicit, let's make sure that our terms are greater than or equal to 0, or maybe strictly greater than 0. So one of the things we haven't really dealt with is how do we deal with terms when they become negative? So we can have sequences where we have both positive and negative terms. In fact, we saw that with geometric. So we want to be able to handle that. So that's our next step, where we're going to say, okay, how do we handle things when we have both positive and negatives? And we're going to see it gets weird. Like, really, stuff that shouldn't make sense is true. And that's going to be a great story. And the other thing that we're going to be heading towards is we're going to start saying, all right, now that we start having a good handle for our sums, our series, what if we start letting us put in some variables? So in particular, we're going to start heading towards what are called power series, where we get x involved. So those are the two things coming up in the next couple of lectures, and they're both good. But behind all that, you want to make sure you have your tests down. And it's not easy, and so practice. The more you practice, the better you get. And, well, have lots of fun practicing. And we'll see you again next time. All right. Have a good day. Bye.